Hello, we were working with this exam question in class the other day and we didn't have time to finish it, so I thought I could try to make a video showing how to solve it and how to write down the solution actually. I wrote next to each part how many marks are allocated for that part. I didn't have that information with me last time in class. So I like this question about the mean value theorem. It starts by stating what the mean value theorem says. And we have discussed this result already, so we know what it means. And we are going to actually see an application of it. We are going to apply it to the cubic function f of x is x cubed plus 3x squared minus 2. And the interval we are considering is the closed interval minus 3, 1. Since f is a polynomial function, we know that this continues on any closed interval we want to consider, so continues on minus 3, 1, and it's also differentiable on the open interval minus 3, 1. To apply the mean value theorem, well, we're going to also need to find what is the value of f at the endpoints. So what is the value of f at minus 3? And this is minus 27 plus 27 minus 2, and this is minus 2. I'm going quickly here because actually we did do this part in class last time. And f at 1 is 1 plus 3 minus 2, which is equal to 2. So, by the mean value theorem, there exists a value c in the open interval minus 3, 1, such that the value of the derivative of f at c is going to be the same as the difference of the function at the endpoints by the length of the interval. So this is going to be 2 minus minus 2 divided by 1 minus minus 3, and this result is 1. The question is asking us to find the two possible values of c for this to be true. The mean value theorem only tells us that there exists one c, there may be more. The question is telling us there are two, find them. So let's write over here what is the derivative of the function. This is 3x squared plus 6x, and we want to find values that make 3x squared plus 6x to be equal to 1. So we are trying to solve the quadratic equation 3x squared plus 6x minus 1 is equal to 0. And we just go ahead and apply the quadratic formula to solve this. So x is going to be minus 6 plus minus, and then we have the square root of 36 minus 4 times minus 3 over 2a, so over 6. This is minus 6 plus minus square root of 48 over 6, and this simplifies to two possible values. Minus 3 plus the square root of 3 times 2 over 3. We're going to call this value C1. And the other option is minus 3 minus square root of 3 times 2 divided by 3. And we're going to call this value C2. Well, we did find two values of C for verifying the mean value theorem. I just want to make sure that those values are really on the interval we want. And you can check with the calculator that this value of C1 is actually approximately 0.155, which belongs to the interval minus 3, 1. And the other value C2 is approximately minus 2.15, which also belongs to the interval minus 3, 1. So for part A1, they ask us to find these two values we found over here. Part A2 asks us to illustrate this result graphically, and I cheated a little bit because I started doing the picture when you were not looking at me. So I have over here the interval minus 3, 1, and I know the value of the function minus 3 is minus 2, and at 1 is 2. And then I need to see how the function looks like, and that I check in the calculator. Okay, you don't have to be like super extra precise, but it looks like something like this. Let's see if I can make a decent picture. Well, this last part is not good. I know I need to get up to the value 2 at 1. Okay, more or less, that's how the function y equal f of x, well, how the curve y equals f of x looks like. And then we have 2 points, C1 and C2. C2 is here, a bit before minus 2, and C1 is just above 0, here C1. And what we have to show is that at those 2 points, the slope of the function is parallel to the second line between the endpoints of the function. So something like this. And then at this point over here, something like this. So we found the 2 points where the slope of the function is the same as the slope of the second line that they have here in red. And that was what we needed to do for part A2. Now we got to part B, which I think is the most interesting, and I encourage you to pause the video and read carefully what part B is asking us to do. Well, if you read it carefully, you probably have noticed that actually the part B2 is an application of the part B1. So in part B1, we showed that under some conditions we can prove that the function is constant, and then for part B2 that says hence, so use part 1, we have to prove that the function is constant. Let me call this function over here f of x, and we have to prove that the function is constant in the interval, on the interval 0, 1, and it takes actually the value pi on that interval. So let me start by checking what is the value of the function at 0. Well, first of all, because we can't do it, and second, because this is good for reviewing a little bit what the function arccosine does. So we have here, I should have written 0, 2 times arccosine of 0 plus arccosine of 1 minus 2x squared. Okay, the function arccosine. I'm going to write 2 important things about it here. One, that the domain of the arccosine function is the interval minus 1, 1. And the other is that the range of this function, so the interval where we restrict the cosine function to be able to find an inverse, is the interval 0, pi. Now, we need to check that what this function is. Again, here I should have written 0, not x. Let me correct it here. So here we want to see in this part over here what is the value of arccosine of 0. This is going to be a value y with the property that when we apply the cosine function to y, this result is 0. And this y has also have to be a value between 0 and pi because that's the range of the function. Well, cosine of y is equal to 0 on that interval for y equals pi over 2. So we have this first term of the function solved. Now let's look at this term over here. This is actually just arccosine of 1. And this is going to be a value y. Again, we know in the interval 0, pi. And we know that cosine of y has to be 1. That's what 1 minus 2 times 0 is. So on that interval, we want y to be 0. So that second term disappears, and we show that 2 times pi over 2 is the value of the function at 0, which is pi. Let's just move this here a bit. Okay, so when we apply the function f, in the second term, we are considering the composition of y minus 2x squared and then the arccosine function. So I'm going to check how the function 1 minus 2x squared looks like. I need that because I need to make sure that I don't go out of the domain of the arccosine function. But actually everything is fine. That well, you can graph that function very easily. The vertex of this 1 minus 2x squared is going to be at the point 0, 1. And the value of the function at 1 is exactly minus 1. So it looks like something like this. You can check it with the calculator. This is y equals 1 minus 2x squared. So what I'm saying here is that when I compose x, 1 minus 2x squared, and then arc cosine of this, I obtain a function. Let me call this h. H is continuous on the interval 0, 1. Yeah, it was key point over here that after I applied the first part of the function, I landed on the interval minus 1, 1, so I was able to apply the arccosine function. And it's also differential on the open interval, and that is because we are composing things that make sense compose, and both the pieces that we are using to compose this function are continuous and differentiable. And so we can add here that so is the function on the first term 2 times arc cosine of x. So what I'm doing this, that's because we are trying to apply the part B1, which says your function has to be continuous on the closed interval, differentiable on the open interval, and it has to have derivative 0 for all the points in the open interval. So now our goal is to check that that's true. So we need to find what is the derivative of the function f. I'm going to pause here and I'm going to wait for you to do the computations. Okay, if you want, you can check my computation over here. I'm not going to go over it. You can just check that if you have some doubts about maybe the chain rule in the second term. I did get that the derivative is equal to 0. So now we are ready to say that by part 1, we can conclude that f is constant on the interval 0, 1. And since f at 0 is equal to pi, we already checked that, then f of x is equal to pi for all x belonging to the interval 0, 1, including the endpoints. So we use part B2, we used part B1 to prove part B2, and now we are ready to work with part B1. Okay, now we are ready to finish question B by doing the part 1. So what we're going to do is to consider the function f restricted to any interval x1, x2. X1, x2 has to be inside our original interval AB. And we apply the mean value theorem to this function restricted here. We are in all the conditions to apply the mean value theorem about the continuity and differentiability and everything. Then we know that there exists some value c belonging to the open interval we are considering, x1, x2, such that the value of the function, the derivative of the function at c is f at x2 minus f at x1 over x2 minus x1. But this is 0. The function, the derivative is everywhere 0. So what we are saying over here is that f of x2 is equal to f of x1. And that was for any values x2 and x1 that we wanted to consider. So then we can conclude that f is actually constant. And we are done.